Okay, so I just want to make a small adjustment here to see if we can get better result. Okay. All right. So what we had so far. Before we broke for lunch, we had the sphere field relaxations or the sphere field pushing out, and the bending resistance. Okay. Now you might notice in the input parameter we have something called the collision weight and the bending resistance weight, but we haven't used those two values yet. Okay. So in effect, they are having the value of 1. The way that we do it now is as if they are having the value of 1. Okay, so how do we integrate this extra weight? So this is a mechanism that allows the user to have more controls over the relationship between the different strength of the move vector. So you can make the bending resistance like 10, which is like stronger relative to the collision weight, for example. Okay, so how do we do it? Now, the actual modification of the code to make it happen is like very simple, but in order to understand why it works that way, then I have to expand with a little bit of diagram. Not this one. Okay, so here's the question. Okay, the pawn is black. Let me change the color so it's easier to see. Okay. All right, we have a vertex, and the vertex. Now you know by now the way we kind of evolve the system is that we apply different move vector on the vertex, right? So let's say that this vertex is being subject to free move vector. Okay, so the total weight move is basically C plus B plus A divided by the total weight, which is free, right? So each time we add a new vector, remember we add 1. Okay, so that will tell us like keep track of the count. And then at the end of the day, we take the total sum vector, the total wasted move, divided by the total weight, which basically equal to this math. So the final result is basically a vector that is a blend result between these three vectors with the blending ratio 1, 1, 1. So the final vector that we use to move the pawn is basically A plus B plus C divided by 3, right? That's what we have in effect. And this is, you can think of it as we combining this free vector into one single average vector using the ratio, the combination ratio or the blending ratio, if you like it, 1, 1, 1. Okay, so this is almost like we take 1 of A, 1 of B, 1 of C, multiply them together and divide by 3. Now, where did this 3 come from? 3 is actually the sum of this ratio here. So, you know, it's like a pie, and you cut into 3 parts and you give each guy a part, an equal part. Okay. Now, looking at the way that we combine the vector this way, we can answer the following question. What if we want to blend the vectors in a ratio that looks something like 2, 1, 1, which it basically means that we want to make this vector twice as important. We want to make A twice as important as B and C. So the final vector that come out should steer toward, should be in more or less in the A direction than in the B and the C directions. Okay. And if you kind of relate it to the way we move, so let's say that A is the vector that the bending resistance forced the point to move to, while B and C are the sphere collision vector. By making A twice as strong, we essentially give more priority to the bending resistance than the sphere collisions. Okay, that's how we control the final movement. Okay, so what if we want to plan with ratio 2, 1, 1? It's basically the average vector will now be 2 times A plus 1 times B plus 1 times C divided by 4. And where does this 4 come from? It's basically the sum of all the weights. Okay, so far we keep the weight as 1, so that's why the sum is equal to the count, basically just a number of vector. But if the weight is not 1, then we just simply add the weight up. Okay, and then we will get the right combinations. Okay, and how about if we plan according to ratio 3, 1, 2? Yeah, we just multiply the weight into the move vector before we add it to the total weighted move, and then at the bottom, the thing we keep track at the bottom is just the total weight. Okay, and the total weight so far is we could just add 1 to it, but now we actually is supposed to add the real weight, which can be different from 1. For now we just pretend that it's 1, but actually it can be different from 1, and this is the way where we can make this. In this case, the vector A is like 3 times as important as vector B. Okay, because the final result will look more like A than does it look like B or C. Okay, so we're gonna change the code a little bit. So now let's go to the process collision. Process collisions. Okay. So before we add the move to the total weight, we have to multiply it with the custom weight, right? So the weight is stored in I collision weight, multiply by move. Okay. Oh, sorry, not I collision weight, just collision weight. Okay. So, but the values actually came from outside. Okay, but we started in this variable. And same here, collision weight and move. Okay. And the total weight, so we add in now is not 1.0 anymore, but actually whatever the value of collision weight is. Okay.
You can also just multiply the move there at the end.
Yeah, actually, you can do it right here. I just write here so that it looks more like the formula on the slide. People understand it easier. Okay, we do the same thing for the bending resistant weight. Okay, so if you look at here, so far we treat this thing as if it has been 1, but now we just, instead of having 1, we replace it with the real value, which can change when we can change according to what the user wants. Okay, so let's go to the bending resistance. If you want to browse through the whole list of methods, if it's so difficult to navigate, you can go here, the drop-down list. It will list all of the member of the class that you're looking at, and you can find bending resistance. And you can click and it will take you right there. Alright, same here, scroll down at the move. So so this is the vector that this guy has to move, right? We have to multiply the move vector, so the entire thing here, put it in bracket, okay, and multiply it with the bending resistant weight. Multiply. Okay. And finally, replace the number 1.0 here with the bending resistance weight. Okay. All of them. So that is the correct math.
Let's say the bending resistance, collision. But I just did it before. Just multiply with multiply with like this collision rate. But also you first have to, if you missed it, the collision rate and the bending resistance, you have to put them into the system, the mesh field system.
Okay, now let's build a system, and you can play with the slider, the bending resistance weight. So you can effectively turn off the bending resistance by setting the weights to 0. Because if you imagine the bending resistance is 0, then there's nothing to move. The move vector is 0, and then the total weight, the count is also 0. So as if it had never existed to begin with. Finally. Okay, and your math will behave a bit weird. I actually realized we have another mistake, but we will fix it in a second. Okay. Anyway, there's a small bug we need to fix. I just realized it. Like in the bending resistance, our normal vector, one of them is flipped, one of them is wrong. The NQ vector is wrong. The NP is vector IJ multiplied by vector IP, but this one, it has to be vector IQ multiplied by vector IJ, otherwise it will be flipped. Okay, and if you remember your high school math, if you look at diagram again, this is the correct order.
I spent all my break to find this.
Oh, you figured it out?
Yeah, and I thought it's just you who had this.
It's
Because like everything might be flat.
yeah, flat, but it's not flat in a 180 way, but flat in a 0 way, right?
Yes.
Okay, so it's because if you swap the order of the vector, the vector will be the normal will reverse, and then if you sum up two of them, they will give you a 0 bending. Instead of forcing the triangle to open at 180 degrees, it will force them to close up at like 0. So it's a small mistake I had. Yeah.
Can you zoom out a little bit to show everything?
Yeah.
Where
So it's in the process bending resistance, okay? And this happened right here. Fix this line. Line will compute and
So the order matters?
the order matters because if you remember the cross product from high school, if you A cross B is the exact
the
opposite of B minus A. Yeah. Okay, now if you run this thing without any growth, you should see that the entire mesh will try to be flat, completely flat. Okay. Okay, so this one I run this surface without any growth, just the bending stiffness, the bending resistance, and you see that it becomes flat, right? Like it becomes completely flat. Okay. So it starts non-flat, and then after a while it's flat. So this is now the correct version. Okay, now if I add in the growth, it should grow out in a more correct manner.
What are your values for
Which one?
to the left? Yeah.
3 and 0.4. Yeah. But there's some random number, so you will not get identical result anyway. But it's a good starting point. Okay, and if you try use a very small value of bending resistance or turn it off completely by setting it to 0, then you will have a very weakly result. If you bump up the bending resistance, you will have a smoother and larger kind of petals or sections on the overall mesh. So this one is without bending stiffness. Everything is really fold crazily. There's nothing to spring them back to the flat configuration.
So if growth is turned off, is it intersect with itself?
No, not necessarily.
Or the line intersect?
It might, but not necessary, because we're still missing the F-lane constraint. If the sphere pushes our way too much, then all the sphere can go through the gap. Okay. Okay, I hope everybody get the result more or less like that. Okay. Now you can change only the parameters why the thing is running. So here I don't have bending resistance, so they fold a lot. But if I increase bending resistance, you will see how they will try to flatten out, like live. All right. So the next and the last constraint of behavior is actually very simple. We just visit its edge. If the edge is longer than the collision distance, then we try to string it back to the collision distance. Okay. So let's go to the update functions. Okay. Again, if you don't know, it's difficult to browse, you can either do Control F and search for it, or just look at the drop down list here and look for the update. Okay, so process banding resistance. Now we have to process the so-called edge length constraint. Okay, so let's make a new function called process edge length constraint. And I'm not sure if in my code I call it constraint or constraints plural. So let's, oh, it's singular. There's no s. Okay, so just constraint. Okay. And of course we haven't defined this function yet, so it's complaint. So let's make a new function right here. So private void process edge length constraint. Okay, now we're gonna again visit each edge. Okay, so a for loop for in I equals 0, I less than pt mesh dot half edges dot count I'm sorry, I'm actually using k, not I, so the counter is k. Please change everywhere because I and j are used for the vertex index, so we don't want to use k. Yeah. And k plus equal to, okay, so this should be similar to before. All right, we get the start vertex of this edge and then the neighbor one. So let's see. Okay, so the index of the start vertex is int I, so that is the start vertex. Int I equal to into pt mesh dot half edge as position k. So this is the half edge, right? And then we say start vertex. That will give the start vertex of half edge k. And then the end vertex is the start vertex of half edge k plus 1. Okay, mesh dot half edge k plus 1, which is the sibling one. Okay, and dot the start vertex. Okay, now we retrieve the actual vertices and check to see if they are far away, if they're too far away. So on 3D vi equal to pt mesh dot vertices at position I. Okay, and we have to convert it to pon 3D. Okay. And the same with vertex j. Okay. Okay, now if the distance between these two vertex, vi dot distance to bracket vj, vj. Okay, if that distance is less than the collision distance, then it's fine. I don't need to bring them back because they are still overlapping. So I should let the sphere acceleration push them out. Okay, So which means that I can skip. I say continue. Okay, skip this edge. Okay, otherwise I have to move them. Okay, so let's work out the vector move. So if they far apart, how much I should move them so that their length, so I should move vi the exact same amount of vj, just opposite way, so that the distance end up being exactly collision distance. Okay. So the move vector going to be vj. I have to be careful with the direction now. So it should be vj minus vi. Okay, so this vector will make I move toward j. Okay, so that is the overall direction, but the actual length gonna be half the way, only half the way to the target. So we have to say move multiply by, and if you work out a map, I believe it's the current distance, which is move dot length, which is this is the current separation, subtract by the collision distance. This is how much they have moved, multiply by 0.5, because you know each vertex should only have to move half this much. Everything divided by move dot length. Okay, because that is the unitized thing. Anyway, you can work it out on a piece of paper, and you will see this is the right amount that they have to move. Okay, now we add the move vector multiplied by the edge length constraint weight. Okay, remember now every time we add a move vector, we have to like consider the weight, which is no longer 110, but like a custom number. So the total weight move for vertex I, okay, because we are dealing with vertex I and j here, so vertex I gonna be plus equal move multiplied by the edge length constraint weight. Okay. And the total weight move for the vertex j gonna be the same thing, but like minus. Okay, so minus equal to move multiplied by edge length constraint weight. And then we have to add the weights to the total weights as well. So total weights I plus equal to edge length constraint weight. Okay, so in practice, when you actually run it in Grasshopper, normally I set this to 1. We just need a small amount of it to make sure that the edge will never go too long. Okay, so we don't have to make it too big. 1.0 is actually usually good enough.
Is that total weight j minus equals? Or
No, the weights we always add up. So this is actually, so if you look at this one, it's few minus, but it's actually plus and then minus. Okay, this is actually how it happened, but and we know this equivalent to this. Yes, exactly. Okay, so I hope this part is quite clear. So normally I would do this part first because it's easy, but the visual effect is not that crucial compared to the other mechanism. So we put it here, and then we build and then test it. Okay. Okay, if you need my help, let me know. Okay, obviously we use a very high bending resistance here, so they try to be like really flattened out. Okay. Okay, anybody else need help? Okay, good. All right, so now the last step is to make this thing like go significantly faster, so you can, you know, get up to 10,000, or I mean 10,000 is possible, at least on my computer, like at an interactive frame rate. If you can go up to 50,000, it's just like not for interactive. Probably each iteration will take like a few seconds. Okay. But anyway, so how do we make things faster? Okay, first we have to work out the bottleneck. So the bottleneck is in this, so the collision checking between the sphere, because basically every sphere you have to, you know, manually and exhaustively, or like using brute force method to check that sphere against the other one. So basically the problem, if you have 1,000 sphere, you cross check with the other 99, you end up with like a very large number, and this is why it gets worse. So at first it runs really fast, and obviously it will get slower over time, all right? But the rate at which it's getting slower seems to go up faster than the number of vertex appear. So if I double the number of vertex, things seem to slow down not by twice, but by 3 times or 4 times. Okay, so the rate at which this thing gets worse is like worse than we expect. Okay, and why is that? Because the relationship between the number of vertex and the time it takes to do the comparison is a square relationship. If you double it, you end up with 4 times more comparison. If you triple it, you end up with 9 times more. Okay, so we have to find a way to do it more smartly. Okay, so if you have a bunch of points of vertices in a space, and let's say that you are looking at this vertex and you try to compare, you want to find which one is colliding with. Okay, so this is the collision like radius. Okay, if you compare this one with the other one, or basically the problem is nobody knows as finding the neighbor. So finding, if you are here and you want to find all the neighbor within the range. So far we do it using brute force search. We have to compare the distance between this guy and all other guy and see if they are below the collision distance or the collision radius. Okay, a more optimized way to do this, is using the spatial grid, which means that before we do the collision checking, we pre-organize all of the points in a grid. Okay, we're not going to implement this method. I've just like describe the overall like approach in plain English, but we're not going to code it up. So don't worry about the implementation for now. We pre-organize into a grid. Okay, and this grid will quickly tell us to eliminate the far away one. Okay, so here, looking at this, I will say that I will only need to consider this square, this square, this square, this square. I don't even have to compute the distance between me and this guy because they are not in the relevant cell. So I can like eliminate a bunch of comparison way in advance. Okay, so it's kind of simple to understand, but it's not as efficient because first you don't know what is the size of each square. It really depends on the density or the relative size of your mesh, right? And if you're unlucky where you have a lot of points in one cell and no points in the other cell, then sometimes you end up with a lot of comparison, and sometimes you don't have any comparison to do with at all. So it's not the most optimum or predictable result that you will get. A slightly better way, so this is actually native to Rhino Common, is to also use the grid idea, but a much more clever way to do the grid. So in the 2D version, this way of organizing a space into little cell box is called the Quadtree in the 2D version, and in the 3D it's called Octree. So again, we pre-organize things into space, but we're smarter. So first we divide the overall space into 4, okay, and we go in and say, okay, this here it has 4 points, okay. My goal is we need to subdivide this space into 4 smaller things until each cell contains no more than, let's say, 2 points. Okay, so I subdivide. Okay, this guy 5, 2 point, 2 point, no point, no point. That's it. This one I subdivide into 4. Okay, this one is okay. I don't need to subdivide any further. This one I don't need. This one I need to subdivide further, and now I'm fine. So my point is that I pre-organize it into cell and space, so that they have no more than 2 points. Okay, and the reason why I do this is, again, checking which cell you are nearby is much faster than checking each individual point. Okay, so by looking at the cell, I can quickly conclude that I only need to consider the point in this cell, which is nothing, nothing, nothing. Okay, and quickly eliminate the other one. Again, we're not going to implement this, but in right now there's a component called Octree that basically behind the scene is use the same algorithm to quickly tell you which point is within the range that you are searching for. Okay. Well, that's what it looks like in 3D. It's called Octree for obvious reason, because each time you subdivide your space into like 8 cells or like 8 branches. Now the KD tree is a smarter way, even better than the Octree. The problem with Octree is that even though it's adaptive, you will still end up with empty cells. Okay, and I can, maybe it's not obvious here, but there can be a situation where this cell will subdivide a lot because there's so many points here, and this cell we have to subdivide a lot, while this cell will only subdivide like a few level and then you're done. And then you end up with a subdivision that heavily skewed toward one region. Okay. Now the next one is much more smarter. We're not going to use this, but this kind of really helpful in order to give you an intuition why this thing will speed things up tremendously, and why the more points you throw at it, the more vertex you have, the more beneficial this strategy will become. Okay, so it's like you get more like benefits as your system grow more and more. So it's kind of a nice thing to have. So this one we also pre-organize into like cell so that we can quickly eliminate which one is irrelevant. But the way we organize them into cell is much more smarter and more carefully selected. So first I look at the space. So this is just a 2D version. So we have only the x and the y dimension, right? I will choose which dimension to divide the space into 2. Okay, so at first the x dimension has like more extension compared to the y, right? So I decide to split the space into 2 cells according to the x. So I end up with the left cell and the right cell. Then I go into each cell and I say, okay, so this guy currently, the y, they span more in the y direction. So I will choose the one. Oh, by the way, I missed one step. So I choose the x dimension to split, and I place the splitting line right at the middle one. So there are 9 here and 9 here. So this guy, if I place the splitting line here, I will end up with 2 cells that contain almost equal or equal. They can be different, but only at most 1, right? If you have an even number of points and you place a splitting plan, the splitting line at one of them, then you end up with 2 branches that differ by only 1 unit. Okay, so you have a very balanced separation. Okay, the problem with Octree is that you end up with unbalanced separation, but this one, because we intentionally split it right in the middle one according to the x coordinate, we end up with balanced tree. Okay, so now we go to this one. So now we have to like repeat the same process with each of the branches. So we go in this branch, and clearly this is the y dimension is the more dominant one. And then I ask myself which one is right in the middle according to the y dimension. So this one has the middle y value, right? So I place my splitting line here, and this space is now going to 2 with again equal or almost equal number of points. Okay, so again I have a very balanced partitions or like or space segmentation. All right, here again the y dimension seems to be dominate, so I short them among the y dimension, and this one is right in the middle. So I place my splitting planes here, end up with 2 more balance. Okay, right, again split, and then I go to each of the cell and I skip splitting them until there is no more thing to split. Okay, and okay, so I pre-organize the space. It takes some time to compute this, but you know it's still faster than brute force search through everything. Okay, now after I pre-organize everything into space, I can, and let's say that forget about this slide for now. Let's say that I'm here and I want to search for my neighbors. Then it's very easy. This is my searching neighbors, right? And first I check if these neighbors overlap with the right cell or the left cell. In this case, they overlap both, unfortunately. So I have to check both cells, okay? But most of the time, you can eliminate half of the points already, okay? So let's say I go in the left cell. The left cell, the next level, the subdivision is this one, right? Oh, looking at this, I already eliminate this cell entirely. I don't even need to do the dot distance to command. I don't say like my point dot distance to, okay? And I only compare myself to this one. So overall, the compared to the brute force, it's faster because essentially every time you, with one step, you generally eliminate half of the points, okay? So the number of points that you compute is quite fewer, okay? So look at the depth of the KD tree. So if I have 16 points, if I split them into two halves, I have with like 8 and 8 on my left and my right, right? And if I split them further, and you see I have 16 points, which, okay, quite a lot, but I only need to split 4 times in order to fully have a really organized space, okay? If I have 1,000 points, 1,000 seem large, but 1,000 you need to only split 8 times and then you fully organize the space, okay? So that's intuition is important because the space you can have a lot of points, but the level that you need to split them is actually grow very small. And when you shirt, you basically start from the top and you decide to wear the shirt from the left or the right, okay? So basically your shirt time, instead of visit to every point, you just follow the tree. So at maximum, you spend about like 4 units of time to travel the tree and collect the one that closer to you. Okay, so overall, your shirt time is the depth of the tree, proportional to the depth of the tree. Okay, while in the brute force, your shirt time is proportional to the number of points. And if we do a quick comparison, the brute force, if you have n points, you have to shirt through all of them. So your shirt time is proportional to n. Oh, that's obvious. If you use the KD tree, your shirt time is proportional to the depth of the tree, which, okay, might not be obvious to you, but mathematically it's just log 2 of n. Now, the mathematics is not crucial here, but the takeaway message is this. N grow much faster than log 2 of n. Okay, so if you compare the speed of factor of the two versions, this is the ratio. But the ratio is not the constant. The more points you throw at it, the higher the speed of factor will be. So if you, at the beginning, if you have only 10 points, the speed of factor will be 1, so which means that you will not be any faster, frankly. But if you have 1,000 points, the speed of factor will probably be, let's say, 5 times. But if you have 10,000 points, the speed of factor might go to 8 or 10 times, okay? Because this ratio, it changes. If you put it as n increase, this thing grow. And this is much better than using multi-threading parallel computation, because if you have an 8-core computer and you run everything on 8 cores at the same time, the speed of factor is what? 8. It always stays at 8. The only way to have more power is to buy more processors, okay? But with algorithmic optimization rather than hardware optimization by buying more computers or more processors, then the speed of factors actually goes up when you have more data to process. So it's actually, in a way, it can outperform 8 cores. So if I run the KD tree shirt on a single core, it can easily outperform a brute force version on 16 cores or 20 cores, provided if I have enough vertices. Okay. All right. So that is basically just an intuition to give you why it's beneficial to do this kind of thing. If you want to have an interesting mesh with like sufficiently large number of vertices to give you a lot of details and geometry, you need this kind of thing to speed it up. Otherwise, it's impractical. If you have like 10,000 points, it's like just impractically slow. All right, so that's the KD tree, but we're not going to use the KD tree. We use even more sophisticated and even better performance. And again, so this is the one that we're using. It's already implemented in Rhino Common. We just need to use it, okay? But let me describe how it works behind the scene, okay? It seems complicated, but we don't have to implement this from scratch, okay? We just use it. All of the tricky part has already been implemented, okay? So the R tree in Rhino Common, the advantage is that, so with the KD tree, as you can see, it can only store points, okay? But what if you want to store object that has finite size rather than points? Then the R tree is really suitable, because the R tree, what it stores is the bounding rectangle. So if you have a teapot here and then a rabbit here, and you want to organize them to a map, first you compute the bounding box and then you pre-organize this bounding box into a hierarchy, as you will see in a moment. All right, so the way it works is that it tries to group the bounding box that represent each object into triangles, into rectangle. The R here stands actually for rectangle. Okay, and the rectangle is tried to be as even as possible. Okay, so it's even on both sides possible and as little as overlap as possible. So here there's no overlap. You clearly separate between the two spaces. Its rectangle will be subdivided into more and whenever it's subdivided, it will have some sort of like smart algorithm behind the scene to minimize the overlap. Okay. And now if you have to search, if you are here and you want to search which one is relevant to you, you can see that you can eliminate the space very quickly. Now this is quite complex behind the scene. All of these, like how to choose which is the best grouping is it's a bit tricky. So, but don't worry, we're not going to have to worry about that. Okay. Octree is like a pretty standard common algorithm these days behind like all of the mapping engines. Okay, so imagine like you are using Tinder and you want ask Tinder to find all of the potential partners within, let's say, 500 kilometers. The last thing you want Tinder to do is to manually search to every single person on Earth and compute the distance to that person and have an if statement. And by that time you probably already go to sleep. So. So what it does is that it pre-organizes all of the entry point into a map, and then if a user in America say search all of the relevant like partners or let's say restaurants within this space, then it can quickly eliminate the entire Asian, for example. Okay. Now Tinder is actually not a good example because people on Tinder tend to like change the location, not that much. But imagine if you organize buildings on Google Map, the building usually don't change that much, so the map doesn't have to be updated that often because this Octree structure itself takes some cost. But if the structure doesn't change much, then you have a pre-organized map, and then if the next time you go to Google and say search all of the gas station within like 5 kilometers, it will answer it give you the answer very quickly, for example. Okay. All right, now we're gonna use the Octree, okay? But so using the Octree in random comment is a bit. This one tricky part because it requires learning a new C# syntax. Now, rather than introducing that part and then confuse you too much, I will just like kind of show you how to do the code, and I will give you like intuitions about this kind of syntax, okay? But if you don't fully understand that, don't worry, okay? So. Let's go back to our code. All right, so we have a function called process collision, right? Let me collapse everything so that's cleaner. Okay, so we have process collisions, and process collision is basically the code here. Now we make another version called process collision using Octree, okay? And we're gonna choose between these two versions based on the Boolean flag. So the user will assign a value here, use Octree. If use Octree is true, we're gonna use the fast version. Otherwise, we use the brute version of the process collision, okay? So let's scroll down. All right, so process collision, right here, we will say if use Octree, okay? If use Octree, then we use the fast version, which is process collision using Octree, which we haven't defined yet, so there will be a little error notification there. Process collision using Octree, okay? Else just process collision. Process collisions, yes. Okay, now we need to define the function. So private void process collisions using R3. Okay, so the first step we need to build the R3 and populate points, populate the R3 with the vertices. Okay, so as I explained, when I explained this in the PowerPoint slide, I use rectangle, but the R3, if it can store rectangle, of course, it can also store points with like zero size bounding box. So in Rhino common, there is an object data type called R3. So we're gonna create an object of type R3. So R3. Okay, so capital R because it's a type name, so it's always capital. And then the variable that stored at 3 is R3 with lowercase r but capital T. And then we use the new keyword to construct a new empty R3. No, R3 is like a special class. So R3 is a data type. It's similar to Pon3D. Okay. Programmatically, it's just a class like Pon3D, but of course it represents like an entire tree. It basically represents the structure, essentially the whole R3. Yeah. And at first the R3 is empty. There's no data, but we're gonna populate it with data. And behind the scene, whenever we add new stuff to it, it will automatically organize it into grouping like this, but everything happened behind the scenes, so you don't see it. Okay, so this is just an explanation so that you understand why it's fast. But for you, we just throw things in, and then we will query it. So when we use it, we will just query find only points that is close to my shared circle or shared sphere. Okay. So now we have to actually add the vertex of the plankton mesh to the tree, so that the tree will pre-organize it. So for each mesh, for each point, for each vertex in vertices dot count. Okay, we're gonna say R3 dot insert. Okay, so now we're gonna insert a new point. So we're gonna insert the vertex at position y, at position I, to the tree. Okay. Now, when you insert a data point to the tree, you also specify a custom ID number that is associated to that point. Because what happened is that when the R3 later, when you do the actual searching, the R3 will tell you the closest point by communicating the ID of that point to you. Okay, so vertex I, we should give it an ID which can help us identify later on when the R3, remember, it's going to report the ID of the point that is found to us, not the actual point itself, but just the ID. So a natural choice for ID would be just the number I itself. Okay. Because the number I will uniquely define. This R3? Yeah. It's in the... it's actually, you can use it from Python as well. It's rhino.geometry. So it's just like rg.r3. Okay, so what we store in there is the Pon3D. Okay, but if we read out a vertex, of course, it's just plankton point. So we have to convert it to Rhino common Pon3D. Yeah. First, so to Pon3D. All right. So that is the first step. We build an empty tree, and then we actually throw in the data from there, and the data will be behind the scene will be organized in that little rectangular like kind of hierarchy. And now we're gonna go in and sort. Okay. So let me check. Okay, so what I'm going to do is slightly different from the reference code I have in the completed file. So I will, of course, after today, I will also upload the entire code on the Google Drive folder. Okay, which gonna. Okay, so now with the tree, we can visit each point again and use the R tree to figure out all of the neighborhood, all of the potential neighbors, all the potential points too close to it, to so that close by close I mean within the collision range. Okay. So for again int I from 0 to the vertex count I plus plus. Okay. All right. So we have vertices I. So let's extract the vertex, the actual vertex I. So vi is going to be pt mesh dot vertices I dot 2.3d. Okay. All right, we have to build the search sphere because the R3, when it's search, it takes in the search sphere. So the search sphere will be centered at vertex vi, right? And the radius of the sphere is the collision distance parameters that we pop up here, okay? And that sphere will be, we will send that sphere to the R3, so the R3 will, and then the R3 will find for all of the points within that sphere, okay? So the search sphere going to be new sphere. So sphere is just not a random common type. Okay, so it's going to be vi collision distance. Okay, now before we actually invoke the R3.search function, we're gonna create an empty list of the collision result. Okay, so when the R3 search function operates, as it finds the ID of the point that within the search sphere, it's gonna save that ID into a list, okay, and then later we can look at that list and then we can know exactly which one we are colliding with, which one VI is currently colliding with, okay. So we will say list of integer, so this is the list of the collisions, and we say collisions in indices, okay, and this list is empty at first, okay. New list in, I have a redundant square bracket. Okay, and now here is the some new syntax that you haven't seen before. It's unfortunate that we cannot do it the simpler way, because when MacNew people, when engineers MacNew integrate the R3 algorithm into random common, they decide to use this C# syntax because it provides more flexibility. But in our case, it actually makes things a bit slightly more complicated, because all we want is just to get all of the ID of the point within that search sphere, right? But the way we do it is kind of a bit indirect, but here we go. So R3 dot search, okay, so the search function will take in the search sphere, okay, and so it takes in two parameters actually. The first parameter is the search sphere, And the second parameters is, let me describe it in intuitive. The second parameters is a mini program. It's not a single data like Quadtree. It's actually a mini C# program that will be performed when it found a collision. Okay, so we're gonna have to write that mini program. But that mini program looks very simple. It just get the ID that the Octree report and save this in this list. Okay, but that mini program basically it's gonna involve in some rather strange syntax. Okay, so please bear with me. I'm gonna do it twice, and again, if you don't understand this new syntax yet, don't worry. Last year I kind of introduced it like from the first principle, but I think it's like a bit too much to talk about. So we have two parameters, so I just break the line. This is the first parameter, comma, okay, enter. So this is where I enter the second parameters, okay, which is a mini program that I write in one line, okay, and put in a semicolon here, okay. So all right, the space right here, I'm going to write that mini program that will be executed whenever the Octree find the ID. Okay, this program take in two input called sender, and the second is called argument. Okay, I know it's very weird syntax, but just please follow me. This is just the shortest way to do it, really. There's no other way to do it. Okay, and then the next symbol is equal and then greater than. Okay, so it's just an arrow basically. Okay, so this is the program that take in two input parameters, and this is the body of the program, which is a pair of curly brackets. Okay, okay, so the body is empty now. Okay. So that is my mini program, which I'm not quite finished yet. Okay. Okay, all right, so the mini program, what does the mini program does is when it runs, it has access to the argument. So the argument will store the ID of the points that the search function had just found. Okay, so the search function, again, it just algorithmically find the point, but whenever it's find a collision point, it will run this mini program, okay? And when we read out the args.id, that will tell us the ID. Okay, and we basically just save this ID into collision.indexes. Okay, so collision indexes dot add arguments.id. Okay, and because this is a statement in C#, we have to end with a semicolon. Okay. Okay, just one little more step. This is basically correct, but except that remember we are still essentially doing the football team matching. Okay, so we only collide the sphere I with a potential sphere if that sphere has the ID that is behind I. Okay, so the ID here we only record the ID into the list if I is less than args.id, okay? Otherwise, we will have double collisions because we only allow the sphere I to collide with anything that has an ID larger than I, because that's the logic of the football team matching. Okay, again, if you don't understand the syntax, don't worry. Think of it as a mini program. That the mini program that had custom or a mini function. This is actually a function with input parameters, but except that we don't specify the type of the input parameters. And it's weird because usually we define functions separately, but here we define a function right in place when we need it. So very strange syntax, I know, but it's the shortest way to use the Octree really. Okay, so after the Octree search has finished, at this point, if you look at the list of collision index, at this point you will have the index of all of the points that we're colliding with. and then this part will be identical to well, hopefully identical. So this part we will say for each integer j in the list collision indexes. Okay, so for each j, and j will be the index of the collision points. Okay, so for each of the collisions we're gonna do the same math that we did before, and that math I think is identical, so I think we can even copy and paste from the other from the process collision, but let me double check to make sure that they are really identical. Move. Okay, yeah, we can take this part, copy it. Okay, so again we're in the this is the process collision, the proof version. Copy the body of the for loop. Okay. Okay, we copy and we paste it in here. Okay. Okay, raise your hand if you need me to do this step again. All right. So the code is actually identical, but we can do a few things. This one, we don't need to check for collision anymore because we know that J is the one that's colliding, so we don't need to have this check. Okay. So that's it. If you have that check, then it's still fine, but it's just redundant. Okay. All right. I pray that it will work. It's like whenever I write code that lasts more than what I can see without scrolling, without testing, I feel nervous because chance of having error is so high. All right. So let's walk through the logic again. We build the R tree, we populate with points. All right, and now we actually use the R tree. So we go through each vertex again, ask the R tree to search all of the collision point according to the search sphere, and the search sphere is basically centered around the vertex I that we are considering. And the R tree will basically give us a list of collision index, okay, the list of index of the point it's colliding with, and then we just look at those collision index and do the push out math that we did previously, okay. All right, let's build this, okay. And remember, we already implement the switch when we can switch between the R tree version and the non-R tree, so now you can really see the difference between two versions. So if you let it run for a while until it reaches 1,000, and then if you flip the R tree switch on and off, you can see the difference quite dramatically, I hope. Yeah, it does work, okay. But the effect is only dramatic when you have like about 1,000 or more. The more vertex you have, the more dramatic the speed up will be. You can check it out by looking at the time, okay. Okay. And with the R tree on, you can push the vertex limit to 5,000, okay. Okay, just to be safe, 3,000 for now. Okay. Let's carry on. So, on my computer, at least you can see I have 10,000 vertices here. Let me make sure it's actually 10,000. Now with the R tree, each iteration takes about 200 milliseconds. Okay, if I switch off the artery, let's see how much more slower. Okay, so 200 milliseconds jumping to 2 seconds. That's a speed up factor of 10. Okay, so it's just like some extra line of code. You like make things run 10 times faster. If you use multi-threading, you can make it go up maximum 8 times because you have 8 cores essentially. But here, even like with just a single core, you can like 10 times faster. Okay. Now, the next important message I want to say, I already said it, but I want to prove it here. The more points you have, the more the speed up factor. So here it's like 10 times faster, right? But at the beginning, when you have only few points, the speed up factor is almost nothing, or like usually only 2 to 3. Okay, so if I restart it again, okay, so this is less than 1 millisecond, so nothing being printed out. Okay, just give it more time to grow. Oh wait, so, okay. Okay, 5 milliseconds. Now if I turn on the R3, it's barely faster, you see? But if this thing grow, and if I just switch on and off, you see the contrast between the R3 and the proof of version will become much more dramatic. Okay, how many vertices do we have now? Okay, 3,000. Okay, let me stop the growing, the splitting. Okay, so 100 milliseconds versus 32. Okay, that's the speed up factor of 3. Okay, so it's not as dramatic as 10. So the takeaway message is that the R3 become more beneficial as the system get more and more complex. Okay, and this is something that you don't have with multi-threading, because the speed up factor that you get from multi-threading is depends on the number of cores you have, which is usually fixed at 8 or 4. Okay, and the only way to make it run more faster is to spend more money and buy more processors. Okay.
Isn't collision there?
Huh?
I see collision.
There is. You have to give them some time. But okay. As I said, this is not perfect, so sometimes they might collide. But the best way to check that is to have a clipping plan. Okay, and we're gonna slice through the whole thing. Okay. Well, no. At this slide, there's no 7 intersections. Let me start from the beginning. Yeah. No. 5. Let's see. No. Still no.
Oh yeah.
Yeah, this one. Yeah, okay. Nope.
Oh, come on. That, yeah, it just go up. Yeah.
No,
Go
where?
Up. Yeah. That.
Oh yeah, this one's bad. Damn it. Yeah, okay, we can. So again, this field collision is just an approximate of reality. In reality, things like small molecules that's never go through each other, right? Here we can approximate that using sphere, but it's not perfect. Sometimes things can still slip through each other. Okay. So that is why it's generally good to grow things a little bit, turn off the splitting so that the vertex have more time to split out, and then we can turn back the grow in again. Okay. All right, let's make this thing run live again. Okay. It's kind of cool to see this thing still run live while the clipping plan is active. Okay, if I increasing the collision weight to make the collision more important, I hope they will. Okay, and turn down the resistance, the bending resistance. And hopefully they will eventually split out a little bit. Yeah, they kind of almost separate out. Yeah. All right. Anyway, so that's pretty much the mesh growth system that we did. Now, there's more feature that you can add as an exercise if you really like to play with this. One thing is that you can make it collide, or not collide, but avoid collision with an object. So you can place, let's say, a little point here, like a repulsion point, and you have an extra mechanism that basically, so if this point, if a vertex is too close to an obstacle can be as simple as a point, you have to push it away further, okay? And then by being a little bit creative and playful with placing these obstacle points, you can kind of shape the growth or the mesh in kind of a more artistic and creative way. The collision can also be a line, okay? So at any point, each vertex has to keep like a certain distance from the line, for example. Another thing you can play with is instead of using this mesh as the starting conditions, okay, so this is like simple starting mesh, you can like apply it on a torus, or okay, we can quickly use so if you have with a bird, for example, there is this mesh here called the weaver bird polylized dodecahedron. Okay, so it looks like no, this is just polyline. We want the mesh versions. Let's see. Oh, this is the mesh. Okay, weaver bird mesh isosahedron. Okay. Let me turn off this. Okay, we can use this mesh as a starting condition. So this one have only one face. It doesn't show you the back face, so it's a closed mesh. Let's make it a bit smaller. Radius should be probably 2, maybe 1. Okay, and I'm gonna plug this in as my starting conditions. Okay, probably it's a good idea to run it through this jitter, this vertex randomization a little bit, so it offset the mesh vertex a little bit. Okay, so what you get out is a slightly distorted version of the mesh. Okay, if you make things too symmetrical, then everything will go symmetrically. It look kind of boring. If you give them just some slight randomness, they will look pretty interesting. Okay. All right. If this is my starting conditions, then and press the reset button and let things grow. Okay, if you don't have weaver bird, you can draw a simple sphere and triangulate the sphere. Okay, because our mesh only work with triangular mesh. So if you draw a sphere mesh in Rhino, you get a quad mesh. You have to triangulate it first. Okay. And we don't have torus here, but we can run this on a torus as well and see thing flips quite interestingly. Similar, but there's no back face. So the other one, if you color the back face as red, you will see the red blend in with the white quite nicely. So,
Because it's a surface.
because this is close surface, you don't see the back face. The other one, if you color them differently, you can see it. Yeah. Okay, and let me play with the bending stiffness here. If I make the bending resistance stronger and reduce the collision, let's see if they. Oh, they kind of already pretty equilibrium now, so they doesn't want to move anymore. Collision waste. Oh, let's increase the collision distance. Or you can draw a simple like UV strip surface and then quickly convert it to triangular mesh. You can also okay, let me pause this and slice through clipping plan. Okay, this one looks good. No sharp intersections on the way through. I'll see some like pretty intricate enclavement. Let's go quite deep inside. Yeah, this one's perfect. No collision at all. Okay. Well, you can save this and play more at home. As I say, it would be interesting to implement some sort of obstacle collisions or some sort of attractor point. Yeah, you can do the opposite of repulsion, where you have a little attraction point and the point should probably move toward that a little bit. And as you move the attraction point around, you can see the vertex kind of move toward that. But they always keep the sphere collision and all the constraint in mind as well. So you can kind of have more way to influence the mesh while still keeping everything non-intersecting. Okay, so now we get back to the theory part a little bit, and then at the final I will show you how to use the mesh, the plugin that we have established so far, but we're gonna access them using C# script components and using RM Python as well. Okay, so far the user can only use this. So far the user using the mesh growth system by the custom components that we gave them, but if they know C# or if your friend knows C# or Python, they will also be able to access our library. Okay, and you can apply the same principle to access all the library as well, like including the Kangaroo solver. The Kangaroo solver .dol file in Kangaroo 2, which was written by, which was developed by Daniel Piker. He structured Kangaroo 2 in such a way that you can use it from C# script component and also from Python as well. So let's get back to some like important theory part that I haven't had a chance to talk about yesterday in day 2. So this point is, hang on, let me open the slides. Okay, something that we've seen quite a lot, but we never talk about is the namespace. Okay, all right. So when we write code, almost all of our code, the class definitions always live inside a namespace. Okay, well, the namespace can be empty, in which case you just don't write a namespace, and then the namespace will be considered an empty namespace. Okay, now what is namespace and why is it useful, and why we need to know them? So namespace. Probably the first kind of intuitive reason why they exist is that they allow you to have class with the same name to coexist. Because admittedly, let's look at the class called curve. It's a common English word. Many people will name their class curve, okay, because it's an obvious name. But how you distinguish a curve class that was developed by McNeil people and a curve class developed by, the people at say Autodesk, for example, So the Rhino Common has a class curve, and I guess if you look at the Revit API, the Revit programming library of the software Revit by Autodesk, they also have a class curve. But they are uniquely distinguished from each other because they are stored in different namespace. So if you look, let's say if you have access to the source code of the Rhino Common and you look at the source code for the definition of the class curve, you will see that they are being placed in a namespace called rhino.geometry. Why the one from Revit, I'm kind of pretty sure that they will always name their namespace something like Autodesk.Revit, for example. So think of namespace as a folder, okay? You cannot have a file with the same name in the same folder, but you can have file with the same name but stored in 2 different folders, okay? So this is the folder called Rhino Geometry. Inside there is a file called curve, or like a class called curve, and this is a folder called Autodesk.Revit. That is why they can coexist, okay? And if you write code that use both this library, then even though both library contain the class of the same name, they can be distinguished safely because they are mentioned by the namespace. As if you want to describe the file name, and if it's confusing to your friend, then what you do, you give it a full path. So rather than say my file.txt, you say you give your friend a full name, C/the folder name / and here instead of slash we have the dot, but think of it as like the folder on your computer, okay? Okay, so inside your Grasshopper plugin, normally when we write code, we have to come up with a namespace for ourselves, okay? That is kind of unique. Okay, so we have been naming everything as workshop. So usually the namespace kind of match the project or the Visual Studio Solution name, but it's not like strictly enforced. It's like a convention, but not a rule that you have to follow. Now, normally big company usually prefix all of their code, or put all of their code in a namespace that usually start with their company. That's guaranteed that nobody will have the same namespace. You know, if you name the namespace after your name of your company, and then dot the product name. So in case of Autodesk, because they have so many products, if you look at the API for AutoCAD, for example, usually the namespace is Autodesk.AutoCAD and then dot geometry and then or dot database or whatever. MacNew, apparently they have only one like major product, so they don't say MacNew, they just say Rhino dot geometry. Okay, and apart from Rhino dot geometry, if you look at the Rhino common library, you have Rhino dot Rhino dot display, yeah, and Rhino dot document, for example, but they always prefixed by the Rhino name. Okay, so those are the namespaces that form the libraries that somebody else wrote, and then we just use those library. And in the code, let's say that we are currently write code in our own namespace workshop. Okay, now if you are in the namespace workshop and you want to talk about a class from another namespace, then the official way to do it is to give it the full path name. Okay, if you use to Windows 95, or MS-DOS or whatever, if you're in a folder called on a D drive, if you want to point to a file on another folder, you have to give the full path, right? If you're already in the same folder, you just need to specify the file name. But if you want to specify a file in a different folder, you have to give it the full path. So this is the full path that leads to the right curve. Okay, and this full path will have distinguished between the curve in Revit and the curve in, Rhino. And so whenever you refer to the class name or the type name and the constructor, the official way is that you have to give it the full path. Okay, the full namespace, like the full namespace prefix. Now, of course, it's inconvenient if you have to specify the full name all the time. So what you can do is you can put a using statement. Okay, so if you have a using statement here, then all of the class name inside this namespace will be available to you to use directly without having using the namespace. Okay, so if you say import using Rhino geometry, then whenever you refer to the class curve, then it will be C# will look for the curve class in any of the namespace that you have like import or like put in front. The Revit one, for example, on the other hand, the curve from Revit, because the namespace has not been imported yet, so you still have to like use the full one. Okay, you have to use like the full name. All right. Now this case is problematic because if you import both namespace and then if you use a class curve, then obviously there's no way C# can know which curve you're talking about. So in this case, you still have to use the fully qualification name if you have like two classes of the same name. Okay. But what you can do is we can give them an alias. So you can say that I give this curve an alias. Okay, so from now on, I can refer to that particular curve as Rhino curve. Okay, so we just give it a nickname, so we don't have to type out the full path all the time. Namespace can be nested just like folders. So what we have is the namespace Rhino.geometry, but actually what it really looks like behind the scene is two namespace nested in each other. Okay, but this syntax is kind of nicer to read, and it's just they are equivalent to each other, but this is the one that people use because it's cleaner. So that is how you nested folder. You just they say C/ like my folder / a subfolder inside. So namespace is like very much like a folder or a directory on your file system. Okay. A namespace can contain many sub-namespaces, just like a folder can contain many subfolders. Okay, so for example, in Rhino Common, the master namespace Rhino has the sub-namespace called geometry, okay, and also display and input. Anyway, let's look at some real examples. So the namespace vector, so the type vector 3D and mesh, these are in the namespace Rhino.geometry, and the namespace Rhino.geometry is already here. That's why you can just say curve and mesh without having to prefix them with Rhino.geometry. But let's say if I remove this line, then boom, you have this thing will no longer be recognized. Okay, and you can fix them manually by saying write dot geometry. Now they are fully clear. But of course, if you have to fix it everywhere, then it's kind of annoying. Oh, and also this one, we also have to fix it here. Basically, I have to fix anywhere manually, but of course you don't want to do that. So normally people just import the namespace in advance. Okay, and if you use like code templates, like the when you generate a new code template using one of the templates that we have been installed, like the Grasshopper composer template, then usually the code template will install some of these namespace for us as well. Okay, let me put this back in. Now plankton, of course, the namespace plankton came from the file plankton.dll that we have here. This part of the code came from the file that I prepared for you this morning. So you open it, and this thing is already here. So that's why you don't have to import the namespace. You just say plankton mesh. This one, for example, this one came from this namespace, but of course this namespace has already been imported, so you just say it out. But if you hover the mouse over it, it will actually tell you the full path name. So class plankton mesh. You see? So hover the mouse will give you the full name or the full path of the class. All right. What else? Visual Studio has a nice feature since 2015. So if you somehow, so let's say that you create, you don't have to follow this step, just want to demonstrate. If you create a new C# source code file, for example, using the .NET class library, which template should I use? .NET Standard, cross-platform, .NET class library. Okay. Just for example, I create a new source code file in the same project. I just want to add a new file. Okay, add a new source code file. Class, okay. This is just for example, I have this class here, and inside my class, I want to use the class pon3d. And of course, now here I haven't imported the namespace rhino.geometry yet, so this thing will complain. But but Visual Studio will can figure out where that is, and will suggest a fix. It will say, do you want to add the statement using rhino.geometry there? And if I say yes, it will automatically add it here for you. Okay, so if you can't remember where the namespace is, like if you type in the class, Visual Studio will make the best effort to look at all of the library files here and try to find the namespace that contain this class and suggest you how to fix this error. Okay, so it's pretty nice. Again, it's not something that you can do in a C# script component. In fact, the C# script component does not allow you to import any custom namespace. So if you want to use a class that is in a namespace that is not supported directly by the C# component, you have to type out the full name whenever you want to use it, which is kind of annoying. All right, so now knowing what a namespace is, let me show you another example where the namespace was used. So if we add an icon to this one, the icon will live in the class resource, which is actually in a different namespace. So a project can have multiple namespace. So if I add an icon, I don't have a good icon for this particular mesh growth system, but resource. Add existing file. Okay, let's just use this weird thing. It's not a untitled. Okay, but anyway, so now that thing is live in the namespace mesh growth dot properties dot resource. Okay, so the full C# variable that represent that icon here, that icon that I just import, is in the namespace mesh growth dot properties dot resource and then dot untitled icon. Now let me explain. So all of the project behind the scene, there is a file inside the namespace properties. Now this file is located here. This is a C# file that is automatically generated behind the scene whenever you import some resource like icon or text file to it. You are not supposed to edit this file manually, so you never have to open it or like touch it, okay? But if you look at the source code, it defines namespace called properties. So that's why when you refer to it, you have to say mesgrow dot properties. You might notice that the word mesgrow is being grayed out, which means that you don't even need the mesgrow. Why? Because we are already in the namespace mesgrow, okay? So it's just like a file system. If you are already in a folder and you just want to keep moving deeper and deeper in the hierarchy, you just like keep specify the forward. You know, go into the subfolder. You don't have to start again from like C/folder again, okay? So similar to file system. Okay, now let me return null because this looks weird. And resource, let me delete this resource. Okay. Right, we now have our library. Let me rebuild it once more. Now let's talk a bit about the object-oriented programming. This is something that we avoid talking, but this is useful in make you understand the Rhino command library more. Or when you look at the documentation, you understand it more, so you can use them more effectively. For those of you who have like experience writing class before, especially in Python, so this might be useful for you to know. If you are kind of very new to, so this is like the first time you do this course, this workshop is kind of pretty much the first time you deal with programming or object-oriented programming. You will need some time to kind of revisit this concept to fully understand it. But do we need this one? Okay, so we can start from here, inheritance. So inheritance. Remember, the idea of class is that it provides the programmer like us to have a way to describe custom data type. And why custom data type is useful? Because it's a meaningful way to describe like certain property that's related to an object together. So as we define a class called pyramid, right? That can represent any pyramid as long as they have length, width, height, and base area or base span property. Okay, let's look at an example. Let's say that we want to define a class that represents length animal. Okay, so when you define a class, you have to think of the properties or the variable that the class is supposed to have. So for length animal, we can sensibly assume that any object of class length animal must have a property called name, which is a string. Okay, the variable is called name, but the type is string. It must have, any animal must have weight for sure. They also have leg count. Okay, and they all can perform certain common action. Let's say eat. Okay, that's kind of sensible. All right, okay, and now this is the new concept now. Inheritance. We can define another class, but this class that we're going to define is not independent from length animal. It's a class that inherits from the class length animal. And what do I mean by that? So okay, so let's define a class dog that inherits all of the properties from length animal. So the way I write it is like dog inherit, which is the colon, okay, length animal. Now what happened is that when I write the syntax, then all of the properties and the function that exist in the class length animal will automatically be available inside the class dog. Okay, because dog is a length animal, so anything that a length animal has or can do, a dog should has and can do. Okay, so even if I don't write anything extra here, and when I use the dog class will have also the dot name properties or the dot weight property and the dot eat function, for example. Okay, I haven't expanded the keyword protected yet, but don't worry. It's like we have public and private, but protected. You will see this keyword pop up sometime, so it's kind of useful to know what it means in case you see them pop up in the tooltip or the documentations. So the class dog currently has no extra properties, or they will just inherit whatever come in length animal. Okay. Now let me. So all of the property that is marked public and protected in land animal will automatically be available to dog, but not the private one. So if land animal has a private property for some reason, that private will not be available to the class dog. Okay. All right. Now the class dog can have some extra properties that only dog has, but other land animal doesn't have. For example, dog has a string that describes the breed of the dog that other land animal doesn't have. Okay, so this property is only meaningful to the dog. That's why we define it here, but not in this one or any other class of animal that inherits from land animal. And it has the function bark, which again, this function only makes sense to the class dog, but not to the other land animals. And then we have a class called, let's say, human, which also inherits from land animals. And okay, the class human can also have the extra property that only human has, but other type of land animal doesn't have. For example, I assume that human has a property called nationality. Okay, that's a sensible thing to. When we design a class, that is totally a sensible thing to put in the class human. And then, okay, we have a function called change nationality, for example, or go to university, because I assume that, okay, let's assume that animals don't go to university, only human can, for example. All right. Now, so that is basically the idea of inheritance. So normally we in a complex piece of software, when there's so many classes, it makes sense to provide a class with basic functionality and then more specialized class that inherit all of this functionality, but also with the extra thing, okay? And you will see the real example moment in Rhino Common. This is just like some toy example that I can explain the concept. Okay, so land animal, human inherits from land animal, but the inheritance hierarchy can go deeper. So human inherits from land animal, and we can have further kind of specialized human class, for example, the class architect, which inherits from human. So any object of class architect must have all of these properties and functionality, like including weight, name, leg count, nationality, and change nationality functions. Okay, but architect can also has and do certain things that other human cannot do. For example, architect has a field called architect license ID that the other guy doesn't have. For example, they can presumably do the function design. And then you have a class, let's say another one called engineer, that inherits from human, but now they have engineer license ID, and let's say they can do the action build robot that, let's assume, architects or doctors cannot do. Okay, so some terminology. So this is some terminology that you might encounter when you look at the documentation or when you Google for help on some certain programming libraries, like programming forums like Stack Overflow, for example. So if you have a class dog inherits from land animal, what we say in English is that the class dog inherits from the class land animals, but also the dog class is derived from land animal. So the two words are kind of carry the same meaning, but sometimes you see the word derive or the word inherit, they mean the same thing. Land animal is the parent class, or the base class or the super class of the class dog. And the class dog is the child class or the derived class of land animal. Okay, so if you see those terminology, you kind of know what they means. Okay, let's look at some real example in the Rhino Common library. Okay, so I haven't explained. Okay, so far I have only explained what is class inheritance. I haven't give you a good convincing reason why it is useful and why this inheritance exists to begin with. Okay, you can kind of guess it. It's kind of convenient when you have a base class where all of the things can share in common, and then you have more specialized class that inherits all of its common properties, so it makes things more structured. Okay, true, that's one of the benefits, but just bear with me, you will see more benefits later, like practical benefits when you program with the Rhino Common library. So let's look at the class curve in Rhino Common. The class curve is the base class for many different types of curve. Okay, and they have this property degree. So any curve, no matter if it's a NURBS curve or a polyline curve, they must have a few property. They must have a few dimension, which is an integer. That's either 2 or 3. They must have a property called domain that specify where the curve start and the curve end, the t value, the parameter, the domain. They all have all of the class curve and all of the giant class of curve also have or inherit the functions closest points, okay? And the function points at plus many more. So this is just some of the common one that I can find from the documentations. All right, now if you look at the documentation, they would say that there are many classes that inherit from curve, line curve, for example, arc curve, NURBS curve, polycurve. Because they inherit from curve, they will automatically have the property called dot degree, okay? So when you create a line curve object and you say my line curve in dot, autocomplete will show you the dot degree and dot dimension properties, even though those dot degree and dot dimension was not defined in the line curve, they was defined in the class curve, okay? But because line curve inherits from curve, they will automatically take all of the properties that the parent's class has and make it available to themselves. But the line curve have extra property. For example, the dot line property that describe the actual mathematical line data. Okay. The arc curve. I look at documentation, but there's no like really extra useful information that I can list here. Now the NURBS curve have an extra property. Basically, just a list of points 3D, and these are the control points of the NURBS curve. Which makes sense. Only NURBS curve have control points. The other one doesn't have control points. Okay, so that's why the property dot points or control points was defined in the NURBS curve, but not in the base class curve. Okay, because not every curve needs control points. Okay. And then the NURBS curve also have the function called reparameterize, which change the domain. Reparameterize basically, okay, you know what it means, right? Just change the domain from to the range 0 to 1. Okay, but if you look at, again, if you carry on, if you look at the inheritance hierarchy, it's true that all of these guys inherits from curve, but curve itself inherits from a more basic class called geometry base. Okay, and geometry base is basically the foundation class or the parent class for pretty much all of the geometry type, all of the geometric data type in Rhino Common, like graph, mesh, surface. Okay. And if you go up the hierarchy, everything is inherited from this basic C# language abstract class called object, okay? But anyway, you will see in a moment why it's important to know about the fact that certain thing inherits from other thing in a second, especially in Rhino Common. So why class inheritance is useful? Okay, it provides a template for class definition. Okay, so that's probably the first reason why you think of is make things more organized, because you don't have to redefine the properties that the parent class already have. Okay, and this provides a template for. Okay, this is another example. So when you write a plugin for Grasshopper or for Rhino, this code doesn't teach you how to write a plugin for Rhino, just Grasshopper, but. Okay, but pretty much these days when you write a plugin for software, not just Grasshopper and Rhino, but also like Revit, for example, or many other software in the building, in the architectural and construction industry, the way it works is that they provide a base class. Okay, in this case, GH component, and you or we, as the programmer of the plugin, our job is to define a custom class that inherit from this base class, which acts as a template. Okay, and when we define this class, the template, inside the template, it says that these are the functions that the child class has to define. Okay, so it's a way to force the plugin developers like us to write the code that meets the standard, so that when you plug it in the main program will work, because the way it works is that the component class must implement register input parameters. So Grasshopper, we know that, okay, this is a class that inherits from a custom component, the GA component. So I can safely invoke the function register input parameters. I know that it exists, okay, because it adheres to my template. And that's why, you know, the plugin works in the host software. Okay, reuse code from the base class. This one is kind of obvious because you can reuse a function that was declared in the base class. So, okay, don't worry about that example. This one is the most important because you're gonna see it in documentation. Okay, so let's look at this example. We know that all of the type curve, all of the special type, all of the more specialized type of curve in Rhino Common, basically inherits from curve, right? Which means that when you write a function, if there is a function that ask the user to supply a curve as an input parameter, you can also, when you run it, you can also give it any type that inherits from curve. So here, if I have an arc curve, I can throw my arc curve into the function. So look at this. The function asks for curve, but the function asks for type curve, but I give it a different type. So at first it seems that it will not work. It will give an error message. However, this type inherits from the base class curve, from the base type curve. So the function is still happy and still runs. And you're gonna see this kind of situation a lot in Rhino when a function say that it take in a geometry base. Let's say that if you want to move an object and you look at the documentation and it say the move function take in an object or a parameter of type geometry base, and you panic and you say, what the hell is geometry base? I want to move a curve. Why there's no function to take in a curve? And then at some point you realize that curve is a child class of geometry base, which means that you can throw that in that function. Okay? Let me give you another intuitive example why it makes sense overall. If you write a function that can work with a land animal, then that function should automatically work with dog, because dog is a land animal. So if a function can operate on a land animal, then it definitely should be able to work perfectly fine with a dog. Okay? For example, if there is a function that extracts the weight from the weight of a land animal, then if you give it a dog also have a weight, so it should also work. So that is why this thing makes sense logically. Okay? Okay, this is not so. Just another example. So if you throw in line curve and arc curve, it should work, even though the function asks for the base class curve. Okay, look at the Rhino command documentation a little bit. Okay, look at the way, so the way that the documentation kind of describe this inheritance is that first, let's go to class curve. The search function is like, okay. All right, so the class curve is defined in the namespace Rhino geometry. So see, now you understand what a namespace is, okay? So the class curve, this is the inheritance hierarchy. So the class curve inherits from the class geometry base, which itself is also in the namespace Rhino.geometry. Okay, and the class curve itself is the parent class of a more specialized kind of curve. I think you can browse that by, let's say, sorry. Okay, see, this is all of the class that inherits from curve. You see how it writes? Look at the indentation. So it lists the inheritance hierarchy here quite nicely. All right, the next thing you need to look for is, let's look at the class line curve, for example, and let's see what property that line curve have. Okay, line curve have the constructor, so those are, you know what constructor is. If you look at the properties, the properties degree, and you look at the description, it will tell you, okay, what degree means. Okay, that's kind of obvious, but it specifies that that degree inherit from the parent class curve. Okay, and in fact most of the things here are inherit. Can we find a property that's not inherit? Okay, this property is only specific to the line curve, because all the curve doesn't have this property called line, and line is actually the mathematical description of the line. Start at end. Okay, same with method. Most of the methods actually inherit from curve, from the base class curve. There's almost no additional unique extra stuff. Inherit. Okay, but anyway, you get the idea. All right, now the next thing about the documentation is that now you know what a namespace is, and the fact that the namespace can be viewed as folder that can be nested in each other. Now the namespace, look at the Rhino common SDK. So the namespace, so when you want to browse through the namespace, in the left hand side is basically just the entire folder structure, or the entire namespace structure. So Rhino is the master folder, and then there is the subfolder. So in Rhino geometry, if you click on this namespace, so inside this namespace there is this bunch of class. Okay, Now the Rhino.geometry namespace itself, I think it's the end. So Rhino also, but Rhino geometry have its own sub namespace. Or again, think of this as a folder. Inside a folder, there is more giant folder that contains more file inside. Okay, so this is how you can systematically browse the namespace. Okay, and this is relevant to you even if you program in Python or in VB as well, because the code structure or the way that the library is organized is the same, and this is not unique to Rhino Common, but it's pretty much the same thing for other kind of languages and other kind of programming library, like for other software itself, like Revit or SketchUp. Or SketchUp actually doesn't have a programming API, but FreeSMax or Maya. Sophistic is a rare example because Sophistic is like a very old programming, it's a very old style C++ library, so it doesn't adhere to this kind of modern .NET style of programming. Okay, so now let's see what else we need to cover, otherwise we can move to the final part. Okay, this part is not particularly important. I just put it there for the sake of completeness. But let's move to the to the final practical part. Now, this part, frankly, if you want to watch the explanation, you can watch the video recording from last year, which is available on the iTech Facebook page, and you will understand what I mean. These are pretty straightforward. I just put it there for completion because this is something that you're going to see in the Rhino Common features from the Rhino Common library as well. Okay, so let's move to the final part where I show you how to access. So now we have our meshgrowth.gha, which is the physical file here. Okay, so we have the meshgrowth.gha. Where is it? Okay, this is the file. So this file ends with the extension GHA, but again, remember the GHA file content-wise is identical to a DLL file. So the DLL is the standard extension for a library file on the Windows operating system. Okay, so if you write a code library in C# or many other language, that code file will be compiled and put in a physical file, a physical library file, okay, called DLL. In the case of when that DLL acts as a Grasshopper plugin, we need to rename it to GHA, and the whole purpose of the renaming is that so that Grasshopper can detect that this is a plugin and load that file properly into the software. But in the content inside is just a C# library. Okay, so now I will show you how to access the class that we define inside the C# library. Okay, so the class we were written in Visual Studio called meshgrowth system, right? But that class is now compiled and stored in here. This file can be shared with other people, and other people can access the class, but not the source code. Okay, so they can, for example, if you look at Rhino Common, we can access the class pond3d, and we can create object of pond3d, but you don't see the source code of the definition of the class pond3d. Well, not directly. The Rhino Common is open source, so you can see the source code online. But by looking at just the library file, you don't see the source code, unless, of course, you decompile it and get the original source code. But decompiling is another story, and of course, it's not all, most of the time it's not legal to decompile a programming library. Anyway, so remember this path. Okay, so let's go to let's go back to Grasshopper, and now we're gonna use the C# script component to access the feature that we have programmed and compiled in that meshgrowth.gha. Okay. So let's open in the handout I gave you. Okay, so day 3 handout and using external library. Okay, let's do the C# first. So using external library, C# 00, this is the starting file. Oh dear, my viewport just completely. All right, so here we have the C# script, okay? C# script, which is empty. Okay, the C# script we're gonna our job is to make this C# script access our meshgrowth.gha and look for the class meshgrowth system, and we're gonna create a meshgrowth system object and then simulate, run it, and output the result. These are just the input parameters that we use to run the meshgrowth system. Okay, so it look identical to the other version. Okay, all right. So again, we define a very complex piece of code in Visual Studio compile it, but now we access it, we enter it from the C# script component. Okay. So first we have to somehow tell the C# component that we want to use that library meshgrowth.gha. So right click and choose manage assemblies. Okay. And this is where you can refer or link the C# component to an external DLL library or a GHA. So let's say add on the right, add a new library and point it to the GHA file. So let's go to the library folder. Okay, you won't see the GHA. You have to go here and say show GHA file, otherwise it will only list DLL. So show GHA right here. And select meshgrowth. Okay, and we press OK. And the library will be imported. And if the import is successful, then you can tell whether it has been imported successfully by open the script editor. Okay, and go to the using part, expand the using statement. Okay, these are all the namespace that the C# script component has been imported for us. And if you scroll down, you see that our namespace, meshgrowth, has already been imported for us. This is how you know that the GHA file has been imported. So whenever you link a library file to the C# component, it will look for all of the namespace that have been defined in that library and import them here automatically. So this part is grayed out. You cannot edit it manually. This part is generated automatically by the C# script component behind the screen. Okay. Okay. Now we can access the meshgrowth system class. Okay. So let me explain the code. Okay. Well, let me do some live editing here just to show how autocomplete. So if you type meshgrowth system, autocomplete doesn't work. But if you type meshgrowth system, it should recognize here, and this code should run. Because this class is like available from this namespace, and clearly the file has been imported, so we should be able to use it. But anyway, if it doesn't show up, then let me explain using the PowerPoint slide, and then we can type in together. Okay, so we need to create a persistent variable of type meshgrowth system, right? We did that in Visual Studio, and here we kind of also did similar thing in the C# component. Right now we do it again. So we declare a variable at the scope custom additional code so that it lives on forever. It doesn't like get destroyed after every time the run script function finish. So a private meshgrowth system of type system. Okay. Now you don't really need the keyword private. So by default, when you define a variable, and if you don't use the keyword private, it will be private. Okay. Otherwise, if you want to make it public, you have to explicitly say public. But by default, everything is private. Okay. So that is the persistent variable. All right. And the run script, it takes in a bunch of parameters, right? And the parameters has the I prefix. So if you look at the code, you will know that they are input parameters. So if the user hit the reset button, or if system is null, which always happens the first time we open the Grasshopper file, then we initialize system to a new mesh graph system. Okay, so this should be very familiar now, but now everything is done in the C# component. Okay, so we access the constructor of the class. So the mesh graph system is a class, again, a class defined in our library, but now we can access it outside of Visual Studio. Okay. All right, and we just forward. In fact, I don't mind if you copy and paste the code, because this code should be like very simple and straightforward now. So we just like forward the input parameters to. Frankly, if you type all of this thing in the C# code editor, C# script editor, it's gonna be pretty uncomfortable. So, all right. And then we just call update and finally get the result and output it. Okay. So. Okay, so it's create a mesh graph system and then update it, and then we get a mesh and we output. So we get the same effect as like the plugin, like the custom component that we did before, but this time we invoke everything using C#. Okay, so if you run this, everything should be. Okay.
Has this now the same speed as?
Generally, yeah, generally the same. So you have the best of both worlds. Okay. Okay, autocomplete actually works now, so it takes some time for it to load up.
And just like a spin mistake.
I think mine is better.
It's just like, did you define also the here?
Yes.
It opens the right Grasshopper.
Yeah. I just try to.
And try with the approximate.
Yeah.
Okay, it doesn't affect the.
Is it okay?
System.
Okay, have you defined it down there in the custom additional code? Yeah, this is the
Yeah,
system.
okay. Yeah.
Okay, so so this versions it should run as fast as the plugin version because you know the wait I lost my feed YouTube. Okay, so this version should run as fast as the proper compile component because you know even though this is like C# script, but it just do the very lightweight stuff. The heavier stuff is in the update function, and update function was written and compiled properly in Visual Studio, and we compiled it. Hopefully, you guys compiled it in release mode. Okay, so let's get full speed. Okay, debug mode will run slightly slower. Okay, so. Because now everything is in C# component, so your friend can invoke it from C# and you know they can harvest the mesh result here and keep using that mesh in the C# script without ever leaving the script itself. Okay. Now let me show you to do the equivalent thing but using Python. Okay, so this is like mostly applied to the people who use Python language only. So the Python, of course, is slower than C# in general, but because we only merely using Python to invoke this function, this heavy function from C#, so it should run like pretty fast as well. Okay, so best of both worlds. Now I prepared the file for you, but this might not work in Rhino 5, which okay, it's very easy to recreate this file from scratch. So open day 3, hands out. Using external library, and we have the Python version. Okay. So if you open Rhino 5 and if this components kind of throw an error doesn't appear, does it work for you? Okay. So the Python one again. So all right. So let me show you how to make this Python component see the GHA file and access all of the class similar to C# component. Okay, but it's gonna be Python language obviously, and it was slightly different. Okay, so okay, so this time you have to remember the full path of where that libraries is. I think maybe you don't have to, but okay. So in Python, okay, for those of you who never used Python before, it's up to you whether you want to follow along or watch. But okay, so in Python we import the spatial library called CLR. Okay, the CLR will allow us to interact with the other C# library essentially. Okay, so import CLR, and then CLR has a function called add reference to file and path. Okay, and we give it the path to our GHA file. Okay. And then after this line, you can import the namespace mesh growth. Okay. And now this Rhino syntax, I'm not sure if I ever taught you guys in the Python seminar, but basically it say that import every single class available from this namespace. The asterisk means everything essentially. Okay, and once every class has been imported, we can write the same code. Okay, so when the reset is true, we invoke the constructor to get the new mesh object and store it in the variable system. Now this is the constructor that was written in C#, but we just invoke it using Python, and in Python you don't need the new keyword. And you don't need the semicolon either. This is C# style, so no semicolon. Okay, and the remaining part should be pretty straightforward, okay, for those of you who already use Python. So C# function, but again, just invoke using Python language, and then all of the data stay within the C# script if you don't want to output it, and you can use Python to apply further logic to the final mesh. Okay, so. And then this part of the code should run theoretically also as fast as the plugin version. if you get an error message, don't forget to hit the reset button. If you don't hit the reset button at least once, the system will be null and you will you get an error message. Okay. So. Okay. Let me explain. It's important. So in programming, whenever you write a string or a text, the backward slash symbol is always interpreted as a special symbol. Okay. But here we just want it to be interpreted as just a normal backward slash. And we do so by specifying the keyword R. R will make this every backward slash appear to be just a normal backward slash. Okay. Otherwise, you will have to use double backward slash just to mean a single backward slash, which is kind of annoying. If you go back to slide 3, this line of the 3. So after you choose a smart way to make things go run faster when you. This is the after. So after is just a way to store vertices of each object here and we store in the structure. Everything happens behind the scenes, you don't see it. The structure will make the collision detection very quickly. So if you are here, you want to collide with all the object, the after will quickly tell you which one you don't need to check so far away. This is the name of the rectangle of the region. So the space is really organized into this little virtual box here. The pattern behind this region, the algorithm itself is very sophisticated. The algorithm itself basically tries to organize the space into a box, put them into even larger box, and we try to do it in a way in such a way that as little overlapping between the boxes as evenly as possible. So if you're curious more about the how to use more Python, more about using Python to access C#, you can look at this documentation. This is kind of how to tell you the relationship between. No, not this fine. Where was that? Day 3. So this is where you can find the official documentation of R and Python. So let me explain a little bit. So we call it Python, but Python is just a high-level specification of the syntax, but it depends to different companies and organizations to implement their own version of R and Python. So the original version of Python was written in C++ language. Okay, it might sound weird when I say that the language Python was written in the language C++, but if you think about it, when you execute Python code, that is your Python code is being executed by a secret software called the interpreter, right? Now, in the case of the original version, that interpreter was written in the C++ language. So the C++ program take in the Python text file and execute it. Now, at some point, a guy from Microsoft decided to use the C# language to execute a piece of Python code, and in that process, make Python compatible with any C# library. Okay. So if you try to use our library with other version of Python, it will not work, for example. So this one is called R and Python. So R and Python is the .NET compatible or C# compatible version of Python. And that is the version of Python that's being used in Rhino and in Grasshopper, and also in Dynamo and Revit, actually, because the Dynamo and Revit API are C#, so they have to use R and Python to make it compatible. There's also, unsurprisingly, JPython, which is written in Java, so it can access on the Java library, and it worked very well with web programming because the Java language was originally meant for kind of web programming. Weirdly enough, there's also a language called PyPy, which is like Python written in Python. I don't know why they did it. There is, I mean, if you want, you can implement your own version of Python too. You can look at what the syntax looks like and like write your own interpreter. In fact, let me. Like in 2015, a group of students from, I think, Rice University make a version of Python, and they open source it called TrumpScript. So this is a special version of Python that has the following features. For example, no floating point numbers, so no decimal number, only integers. America never does anything halfway. So all number must be strictly greater than 1 million. Oh, there's no import statement because everything has to be homegrown in America. there's no Boolean value of true and false. You have to use the keyword fact and lie. So they customize Python a lot. Okay. All programmers ever is a great. Okay, sure. If they're running computation from China, transcript will not compile. Okay. All right. Easy to type with small hand. Really. Okay. Okay. Transcript is not compatible with Windows because Trump doesn't like PC. Okay. So basically, it's just the standard. The Python foundations was the one who like specify what the syntax look like and what the basic features should look like, and it's up to different person to decide how to implement those features based on different engines or interpreter. Not all of them will adhere to all of the standards. So for example, here they replace the keyword true and false with fact and lie. For example, it's just like a little joke that they make, but they publish the entire source code for this version of Python. Their slogan was like "Make Python great again" or something like that. Yeah, make Python great again. Anyway, so Python is a popular programming language because the syntax is simple. Now, implement a complex piece of algorithm in Python is a bit painful because, as I explained, the Python language make it very easy for a certain kind of bug or errors to appear that can be easily prevented in C#, for example. But if you just want to use Python to invoke an extremely intensive library like what we did, then Python is really suitable. In fact, this is what artificial intelligence researcher does all the time. They have this intensive matrix multiplication library written in C++, but extremely fast. But those AI researchers doesn't really use C++. They use Python. They create a matrix and they send those matrix to the hardcore library written in C++ that's run really fast. 2 years ago, the researcher at Liga Observation, the one who won the Nobel Prize for discover the proof about gravitational wave, after they won the Nobel Prize, they wrote a letter to the Python Foundation to thank them and explain how Python plays a crucial role in the development, in their discovery, because Python allowed the scientists to quickly, put data together and send those data to the more intensive library. So the library, like the matrix library or the physics simulation library itself, almost never written in Python. It's written in a much more basic and more efficient language. But the user will be able to invoke this fast library from Python. So this is why these days it's still important to know Python in addition to other programming language as well. Python is everywhere because just most of the time, if you're just a scripter rather than a programmer, then your script is pretty short. So in that case, Python make it very easy for you to learn. And because your program is not so big, the chance of making mistake is not that high compared to writing a piece of math system. So doing it in if you have a short script, and there are fewer errors, and if there's error, it's easier to track. Okay, so or to find out, for example. Okay, so anyway, that is the end of the workshop. Thank you for attending. Any question you want to ask before we break up? Thank you. All right. All right, so I'm going to stop the live stream now. Thank you for watching. The video will stay online. We will also edit the video to cut out some of the long posts and some of the part where there's no things going on, and we will upload a more edit and shortened version later on YouTube. Okay. All right. Bye bye. I will stop the live stream now.